Okay. This is the number 16 lectures in the series of the lecture in digital image processing. And today I would like to talk about we talk about different transform, Fourier transform, Hotteling, and not Hotteling, but the other one, HAR, and the different HAR transform and slant and other. And today I'd like to talk about this statistical property of the using a statistical property, which is the Hotteling. This one is Hotteling transform. This is a Hotteling transform. Today I will talk about Hotteling transform. Hotteling transform is based on the statistical property of the vector, and we can call it also we can call it a eigenvector or principal component for KL. Carnot-Lev transform. We can call it's different name, but same. But what is the important? This previous one. The important point is we just it's for transfer. It's kind of the orthogonal transformation. It's very orthogonal because it's based on eigenvalue and eigenvector. And we suppose that we have the population of the point, which is we can call the pixel of the image, pixel on an image. For instance, x1 to xn. I will tell you, for instance, we have n image, and at the same position, we have the same pixel x1 with xn. That at same coordinate, the level of the gray level of for instance, of the image is x1 to xn according to different band of the image. Well, we can call it from band or different. I will tell you about other. With this is statistical. So we define a new vector with x from x1 to xn, n dimension, for instance. The mean value of this vector is mx ex, expected value, is argument of the ex, expected value of x, which is the summation of this, and then for each component, each pixel, and then divided by the number of the pixels. For instance, if you have different image, I will show you maybe later in the Zoom. Maybe it's better to show like this. Yes, it's better to show like this. For instance, we have different band, a spectral band of 1 to 6. So you have different pixels on the same position from x1 to x6, for instance. Then you have a vector of x1 to x6 component. The mean value is estimated by 1 over m summation of this pixel from that the same position, the gray level of this. So this is the mean value. And then at the same time, we can also define the covariance matrix. Covariance matrix is a Cx, if you reduce the mean value from the vector and then transpose of that, and then make the expected value of this two-dimensional, this multiplication of the vertical and the horizontal, which is a matrix. So the result of Cx is the covariance matrix, which is matrix, not the vector. This vector and the Cx is the matrix of n by n dimension. This is n by n dimension. So you can obtain this covariance matrix. With this covariance matrix, a component of Cij, which is Cj, it is the symmetric matrix. And one example, for instance, here, well, M is obtained like this, as I told you. Let me continue like this. And then for this example, we have three components. I mean, a vector with 3, 1, 1. And then with this mx, with this vector, we can calculate if we have, for instance, 4 component, and then we can calculate this covariance matrix from this. So as we see, the main diagonal is highest value because it's more correlated, and this sub diagonal are less. But it is not orthogonal because of it's not perfectly orthogonal. Let's say, for instance, for Cx, we calculate find the n orthogonal eigenvalue of this. Then by order this by we make a matrix like A. The component of this matrix is the eigenvector of this of Cx. So we make a new matrix A, and then this transform the matrix A to the new from X. We map X to a new population, from X population to new population Y. So reduce the mean value and multiply by the matrix by the eigenvectors. And then this is the Hotteling transform. This is from X to Y. It easily we can obtain that because it is a reduction of the M from the mean value. Then the mean value of the new population of the transform, Hotteling transform, or the eigenvector transform, or I mean component principal component analysis. Then the main value is 0, and another one is that Cy obtained from this matrix A from different sides. We can multiply A, Cx, A transpose, and Cy is quite orthogonal, I mean diagonal matrix, as I can see here, yes. So we obtain a new population from C population, from the X population, we obtain the Y population by using a matrix of the component of the eigenvalue. So this new Cy, the covariance of the Cy is quite diagonal, and subdiagonal on 0. So that is the perfect orthogonal transformation. And for instance, I can go back here and show you in detail. Here I was at set to you. We have, for instance, we have 6 bond like this. I can show you 6 bond here. Maybe I can show you at the end. 6 band of the this one. This is 6 band 1, 2, 3, 4, 5, 6. For instance, from the satellite or airborne uh, image of a city. For instance, we have six band. Well, each band from 1 to 6 has a different wavelengths band from this to this. And this is in my micron. So the different band, the sense is different, so we can find different image. But from these six image, we can obtain, as I back here, I come back here, we can obtain this six band and obtain the vector and then covariance and then transpose by the eigenvector matrix A to new set population Y with the component of the Y with the largest lambda eigenvalue at the beginning. So lambda 1 is more than lambda 2 and more than lambda. So as you want, you can cut it and then just send the more meaning because it's quite orthogonal. So it's very important that I can just for reminding, I will tell you that eigenvector eigenvalue like this. For instance, you have a matrix C, and then for this n by n matrix, eigenvector E is lambda E is equal to C lambda. So obtain this with this lambda, which is eigenvalue. This is the definition of the eigenvector eigenvalue. And then from this, after this transformation, if I have the image, I will show you like this. So after this transformation, maybe here, this is before original image is this six one, and after transformation, we obtain first two bands is 1 to 2 has more meaning than 3, 4, 5, 6. It means that after Hotteling or again principal component transformation, we can obtain the more meaningful of the image, these two image with the highest eigenvalue. Eigenvalue of the first is 3,000 something, second is 900 something, and then gradually 3, 4 to 6. The eigenvalue, this is not band, this is eigenvalue. Eigenvalue gradually decrease. So this is the two band has highest eigenvalue. Okay, you have something here. Okay, and then I can show. This is one example, and another example is this is HottelingTransform or eigenvalue of principal components, as I said here. Principal component or K and L transform. Another example, if you can, for instance, make a graph of the different, for instance, a plane like this, and then for each, in this case, we have a vector of two dimension x1 and x2, which is the coordinate of the line on this, for instance, airplane. So you can make a shape of the airplane by this. And then after transformation, goes to the direction to the main eigenvalue, and like this, after transformation become. So with any rotation, you can put the order into the eigenvalue, and at the center is the mean value after transformation. So you can if you give the computer any shape, it can rotate to the always understanding for, so it's good for AI image to understand the shape of the unknown well, an unknown shape or figure. So this is another example. And then also you can compress the with this I mean with this transformation you can compress the image by just taking the first 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 one and second component and then like this I will show you here. First and second components, then you can reduce the it also you can use it for compression. Algorithms for image processing. For instance, if you for instance, if you take only two components, it's more meaning. So you can say that X is also obtained from A transform Y plus MX. So if you take only out of n, you take k largest. If you take the k largest eigenvalue, then the dimension doesn't change like this. So new recovery image obtained from the more meaningful image. So and then it's compressed. So sending the taking the airborne image and only taking the meaningful image and then send with the I mean, with the lower capacity of the component of the data. So it's better to use for image compression. So it is one application is image compression, or another application is, for instance, if you send two components, it's enough. So it is, you can use it for image compression. Also, you can use it for, as I said here, for another application of the Hotteling transform is to make a unknown shape to a just understanding shape like this with only two component x1, x2. So the vector here is x1, x2, and then after transformation, you find the mean value and the orientation is eigenvalue. So that's also you find the shape. These two is the application of the Hotteling or principal component transformation. Eigenvector or Hotteling or K and Carnot law transform or principal component. That's all for this application. Just I show you here. Here, maybe I can show you here. Let's jump like this one, and then find the mean value, and then expected, then covariance matrix, and then this eigen value, making the orthogonal transformation, and then this is the definition of the eigenvalue, and this is the application. One application, and the second application is the application. And that is all for this. The next lecture is for merge enhancement. So I think it's better to stop here. And thank you very much.